First, this video is about introducing a brief introduction about graph theory. First of all, graph theory is about graph. And as mentioned, that a graph is something just like this is a graph. When you do researching or search on something or data research or something, a graph may be like this. And the graph can be represented as graph. V point E. V is the vertices and E are edges. What is a vertex and with the edges? These are vertex with circles around, and edges are just those lines between that. And suppose we have a graph like this. It means 1, 2. Then 1, 2, 3, 4 forms a combination of vertex, and 1, 2, 1, 3, 3, 4. They form a combination of edges. And then we introduce degree. What is degree? Degree is the number of edges incident to the vertex. So for example, degree 1 equals to 2 because there are two vertices, there are two edges. And degree we reduce that D4 equals to 1 because there is one edges incident to this vertex. And now we introduce our first theory is the handshaking lemma. We call it like this, handshaking lemma. It is originated from a group of people shake hands to each other, and each different people must shake each other's hands once, at most once, and at least once, exactly once. So here it comes is sigma I equals to 1 to n because there are n people shake hands to each other. And the summation is degree vi equals to 2 absolute value of edges. That's because there are two people between the two different vertices, one edges and one edge, one edge, one edge. So the number of people shake hands to different people, they are the double of the sum of edges. Because two vertex has one edge. That is the first theory we have in graph theory. And then second is a path. What is a path? A path is different vertices combined with each other with a specific order. For example, there's 2, 3, 4, 5. Then a path must be like 2, 3, 3, 4. And we can't write like this. We can't write like this because 3, 5 is repeated. So there is no repeated vertex and edges in the past. The only thing we can do is that the first you subset A, B, and here the next edge must start with B something else. You should do like this. No repeated edges in a path. And then we found a cycle. A cycle, what is a cycle? A cycle is the definition of path. You mean the path like, for example, A to B, C, D, and dot dot dot, and then back to A. So on the definition of path, a cycle is a path where the ending point and starting point are the same and connected. The definition of connected graph is in a graph between every vertex there is a path. There exists a path between every vertex. For example, this is connected. And if we write like this is not connected because between this path and other paths, there is no, between this vertex and other vertices, there is no path. But if you write like this, then there is path. You see, path between these vertices, there is a path. Between these two vertices, path 1, 2, or 1, 2, 3. For this vertices, 1, 2, or 1, 2, 3, there is a path. So that's the definition of connecting. And aesthetic. An aesthetic graph is a graph that does not contain a cycle. For example, this graph is not aesthetic because here it contains a cycle. But we do like this, then it becomes aesthetic. It not contains a cycle. And a tree. What is a tree? A tree is a connected aesthetic graph. For example, first it has to be aesthetic, and second it has to be connected. So what we use to draw a tree is something like this one, right? This is a tree. Then this can also be a tree, but this can't be a tree. This cannot be a tree because they are not connected. And then we come to the definition of leaf. What is a leaf? The definition of a leaf is in a tree, a vertex with degree equals to 1. In a tree, that is a leaf. So we just copy this graph. Let me draw one. Then what is a leaf in this one? This is a leaf. This is not a leaf. This is not a leaf. This is a leaf. This is a leaf. Then 4 leaves. They all have a degree equals to 1. And next is a theory. There are 3 theories. The first is every tree with at least 2 vertices has at least 2 leaves. Every tree at least 2 vertices has at least 2 leaves. And second is removing a leaf from an n-vertex tree creates a tree with n-1 vertices. And here we suppose n bigger than 2. It is removing a leaf from an n-vertex tree creates a tree with n-1 leaves. And from these two we get the third theory is that for n bigger than 1, then G is n-vertex graph. Then G is a tree if and only if G has n-1 edges and no cycles. So these are the 3 series. What we have to do is just remember this. For the proof of these 3 series, I will show you in the following video shares. And for walk, then what is the definition of walk? Walk is the most general form of path. We can express like this. A path is a special walk. Why do we call it this? Because walk have more freedom. Because in a walk, you can have repeated edges as long as they are placed in order, just like A, B, C, and then B, C, A. You can replace like this. Because they have more freedom as long as you place them in order. That is to say, for this graph, you can go here, a walk can be this one, then from there here, and back to here. For 1, 2, 3, 4, 5, 6, you can go, a walk you can go 1, 2, 2, 3, 3, 7, 7, 4, 4, 7, 7, 5. Although 7, 4 has been repeated twice, then in a walk, there's nothing special about it. There are no contradictions because it's a walk as long as you place them in order. Just as the ends of the first edge is the start of the next edge. As long as you do like this, it doesn't care whether you have repeated edges. The closed walk. What is a closed walk? Closed walk, you can treat it like this. A cycle is a specific form of closed walk. So same to this one, just a closed walk can have repeated edges. You see me like this? But as long as the starting point and the end point are the same, it doesn't matter. There's a closed walk. Then the next theory is an old closed walk must contain an odd circle. What is an odd closed walk? An odd closed walk means the length of the walk equals to 0 or equals to odd number. What is the odd closed walk? First 1, 2, 3, 4, 5, 6, 7. This is an odd walk. And this 1, 2, 3, 4, 5, 6, 7, 8. This is not a closed walk. But this is not an odd walk. This is an odd walk. This is not an odd walk. And the next definition is complete graph. What is a complete graph? It is between every vertices there is edge. For example, for n equals to 1, then we give 1 point. N equals to 2, give like this. N equals to 3, triangle. N equals to 4, 1, 2. N equals to 5. First we draw a 5 degree and 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. It is a complete graph. It's between every vertex there is an edge. And this another definition is bipartite. What is a bipartite? If a graph can be expressed like this, G equals to L, R, and every vertex, L and R, they form every edges in every edge in G. So every edge in G, suppose like E, can be expressed as a form like this, UV, where U is the element of L and V is the element of R. That is to say, if we draw that, we can say this is L point, this is R point. It should behave like this. There is no connection, direct connection between these two, but there are connections between different sides. So if it behave like this, then it is a bipartite. But if we add one more line, then it becomes like this, then this is not a bipartite. because there is just one more, so on the same side there should be no edge. There only be edge between different sides. And the theorem is a part graph is bipartite if and only if it has an odd cycle. Just remember this. I will give you the proof later videos. And that's the definition of matching. A matching is it is something. All the matching have something to do with bipartite. If it is not bipartite, then we have nothing to say whether it's matching or not. Then the first condition is matching is specific to bipartite. And a bipartite is matching is that no two different edges share a vertex. What it means that this is bipartite. This is not bipartite because these two vertices share this, and these two vertices share this. Well, H1, H2 shares this vertex, H3, H4 shares this vertex. This is not allowed in matching, so it cannot be described as a matching. And next, finally comes the Hall theorem that is satisfied for every bipartite. What it's telling is that if graph G has a matching converting L and if and only if the absolute value of S is less than the absolute value of neighbor of S. So just write this. G has a matching converting L if and only if S is less than the absolute value of neighbor of S. So to clarify each element in this series, first that S is a subset of L, and what we call N is the neighborhood of S. What is the neighborhood? That for L, if we choose these three as S and they have A, B, C, D, E, F, if this is connected like this one, then we say that A, B, C, D, E are neighbor of S. Just connected, they are neighbor. For example, 1, 2, 3. The neighbor of 1 is A and B, neighbor of 2 is C, and neighbor of 3 is D and E. And F is not in the neighbor of S because there's no connection. Anyway, that is a neighbor. And this is all about the Hall theorem, and that's the end of every brief introduction about graph theory. First start with the definition of degree, and this is the path. And then it's a cycle, connected, an acidic graph, chi, leaf getting a chi, and three important theories, and a walk, the definition of walk, and a closed walk, and this is another theory, an odd closed walk must contain an odd cycle, a complete graph, this is a complete graph, and next bipartite, and then finally matching and Hall theorem. So that's all about this video. Thanks for watching.